Yo kids, 2016 AS Physics Unit 1, question number 5. This is our momentum and Newton's second law question, right? So it says a law of motion can be expressed as that the resultant force is changing momentum over time. Now we normally think of force equals mass times acceleration as Newton's second law, but don't forget, by definition, acceleration is the rate of change of velocity. And of course, velocity times mass is momentum. So the rate of change of momentum or change of momentum over time is the same thing as F equals ma, which is Newton's second law. Right, onto a graph. Don't forget, anytime you see a graph, really, you're going to be finding a tangent or the area underneath it. The graph shows the momentum of a spacecraft, how it varies with time. Momentum in normal units there, kilograms meters per second, and time in seconds. By drawing a suitable tangent, show that the resultant force on the spacecraft is approximately 2. It's a show that, so we know where we're going. Right, so they've told us that the resultant force is the change in momentum over time. So I'm going to draw a tangent at t equals 1 seconds. There's my tangent there. And then of course I'm going to find the change in momentum. So I'm going to get this value here and subtract this value here to get my change in momentum and divide that by the time taken. The time taken between those 2 points was 2 seconds. The values were 5.8 and 1.7. Subtract them and divide, and I get 2.05 kilonewtons, which is pretty good because, excuse me, they wanted 2 kilonewtons, right? So that's a good show me. Hence, which means you must use that answer from the previous question. Hence, show that the mass of the spacecraft is approximately 5,000 kilograms, given that at t equals 1, its acceleration was 0.4, right? So we've just worked out the resultant force, so this is where we go back to F equals ma now. Rearrange it. The mass is the resultant force divided by acceleration. We've just worked out the resultant force was 2.05 times 10 to the 3. Note there on the graph, right? 10 to the 3 kilograms. Don't forget, if you didn't get that out, it was a show me, so you could have used the 2 kilonewtons there. Divide by the acceleration, which they've just given us, as 0.4, and it comes out as 5,125 kilograms, which is a pretty good for a show me 5,000. Right, then it says label with the letter P, so it's in bold, do what they say, a point on the graph where the resultant force is 0. So if the resultant force is 0, then acceleration is 0, which means it is moving at a constant velocity, therefore the flat part of the graph there. So you could label P anywhere on that point there to get that simple mark. Right, over the page. So we're going to have obviously a conservation of momentum question. Here they ask us for the definition as well as doing a calculation, a nice easy one for 2 marks. State the principle. So the total momentum before collision equals total momentum after. That's 1 mark, provided no external forces act on the bodies for the other mark. Right? Don't lose that easy mark, please, kids. And then they want the velocity of both spacecraft after colliding. Right? So we've just had this graph. And then at 4 seconds, it docks or collides with another stationary spacecraft, right? So this has no momentum because it's stationary, there's no velocity, and they give us the mass, and then they coalesce, join on impact. So calculate the velocity of both after colliding. So the total momentum before the collision will equal the total momentum after the collision. Now before the collision, we go back to the graph, total momentum was 5.4. There it is, right? 5.4 times 10 to the 3. Total momentum before was 5.4 times 10 to the 3. The total momentum after will be the sum of the masses. We've already worked out the maths, but it was a show me, so if you didn't work it out, you could use the 5,000. Add on the 7,000 of the new stationary, times by the velocity, so that's 12,125. So to get the velocity of the docked spacecraft, this divided by this, and we get a velocity of 0.45 meters per second. Right? Not a bad question there. Happy days.